Welcome to the PetroSkills PetroAcademy skill module covering reservoir simulation at the core knowledge level. This section provides an introduction to the module. This module covers the following learning objectives. Describe what kind of data is used by a simulation run. Describe the kinds of information that can be generated from a simulation run. Explain at a high level how reservoir simulators work. Describe how simulation models differ during the life of the reservoir. And describe how models are classified based on the type of input data used and the question the model was designed to answer. We've already talked about reservoir simulation in several different modules making up the Applied Reservoir Engineering course, as reservoir simulation is the only tool in our toolbox that can claim the dubious distinction of using everything we know about our reservoir. The positive spin on this is that reservoir simulation is a great integrator of data. It forces us to look at everything we have and fit it all together in a coherent, physically consistent model. The other way of looking at this is that reservoir engineers fail by getting lost in the details of the data integration. So let's start at the very beginning and state the reasons a model exists. Any kind of reservoir engineering model is primarily to predict the future. We want to know what is going to happen next so that we can plan for it. Unlike a real reservoir, we can move forward and backward in time quite easily. This means that we can use a model to predict the present. Comparing the difference between our model prediction and what is actually happening provides a powerful insight into how well we are managing our reservoir. Our time warp capabilities with our model allows us to try out new things, and if they don't work out as expected, we can avoid damaging the economic value of the reservoir by doing things we can't undo. All our reservoir models can be divided into two types, physical and mathematical. In the 1950s, reservoir engineers actually used to build physical models of their reservoirs using sand, mineral oil, and water. Then they would stick straws into the sand to produce the model. This is an example of a comprehensive model, as we are trying to understand how all the components of the reservoir system interact with each other. We don't do this anymore, but we do take little pieces of the rock out of the reservoir and try to force fluids through them in the lab. This is an example of an elemental model, in that we are only trying to understand how one component of the reservoir system, maybe relative permeability for example, works. Our mathematical models use data and equations instead of oil and sand. Statistical methods are different from the other two in that the equations used do not enforce the laws of physics. The most popular statistical method is probably decline curve analysis. Then there are transforms used to estimate the value of one property from the value of other properties, such as permeability from porosity. Then there are rules of thumb, which are based on experience or the observation of past behavior. Analytical models are based on the laws of physics. We try to simplify the problem we are trying to solve so that the equations are tractable. A great example of this is Darcy's law. The version shown here has three simplifications: a single fluid, linear flow, and steady-state conditions. Then there was the Buckley-Leverett model that extended Darcy's law to handle two fluids simultaneously. Material balance models completely ignore flow in the reservoir and instead concentrate on pressure and volume changes with time. Numerical models try to maintain the complexity of the problem and in turn give up the opportunity for exact answers. Finite difference simulation is the most popular kind of numerical model and the one we will concentrate on in this module. Streamline simulation uses essentially the same model description as finite difference simulation, but is much faster. Resistance-capacitance network models are completely different. in that they model pressures and flow rates in the reservoir using the analogs of current and voltage. We have just briefly reviewed a whole range of mathematical models which can be applied to a reservoir. Some are more accurate than others. Some provide answers more quickly. So, of course, the question arises, which one should we use? The answer, unfortunately, is not the one that produces the most accurate answers, but the one that allows us to meet our business objectives at the least cost. We face the same choice within reservoir simulation, as we can design our models to be very simple and run very quickly, or be very complex and run quite slowly. Here are the topics we have covered in this video. We will delve into reservoir simulation in more detail over the rest of this module.